The spacecraft exists first as a concept of motion, constrained within Earth's upper atmosphere, where air becomes increasingly thin and pressure fades into near vacuum conditions. In this outer region, the boundary between atmosphere and space is not a sharp line, but a gradual transition shaped by altitude-temperature variation and the diminishing presence of molecules. The Kármán line, often used as a reference point for the beginning of space, sits at about 100 kilometers above sea level, yet even beyond it traces of atmospheric particles persist. The spacecraft associated with nuclear-powered exploration toward Mars begins its journey within this layered structure, where Earth's gravity still dominates and atmospheric drag still influences motion. Below this highest boundary, the upper atmosphere contains the thermosphere and the ionosphere. In the thermosphere, solar radiation energizes sparse gas particles, raising temperatures in a way that does not correspond to the sensation of heat as experienced near the surface. The air is extremely thin, so energy transfer through collisions is limited. The ionosphere overlaps this region filled with charged particles created by solar ultraviolet and X-ray radiation. These charged layers reflect and modify radio signals, shaping communication between ground systems and ascending spacecraft. The nuclear-enabled spacecraft passes through this environment within the protective structure of a launch vehicle, where its internal systems remain sealed and isolated from external conditions. At this stage of ascent, the spacecraft is not operating independently in open space. It remains attached to the launch architecture, where propulsion is still provided by chemical rocket stages rather than nuclear systems. The nuclear component designed for later phases of interplanetary travel remains inactive or shielded during this early climb. This separation reflects engineering principles that keep radioactive or high-energy systems stable until they are safely beyond the densest parts of Earth's atmosphere. The outer environment therefore acts as both boundary and filter, shaping the safe progression of energy systems from terrestrial launch to deep space function. As altitude increases, atmospheric density decreases steadily. Molecules of nitrogen and oxygen become widely spaced, and aerodynamic forces weaken. The spacecraft experiences a shift from continuous airflow to a near-collisionless environment where particles are too sparse to behave as a unified fluid. This transition is critical for understanding how heat pressure and motion change during ascent. Near the lower regions of this outer layer, aerodynamic heating still plays a role generated by compression of residual air against the vehicle's surface. Higher up, this effect diminishes, and thermal control becomes more dependent on internal systems rather than external interaction. The nuclear spacecraft concept, as studied in modern space engineering, often involves a compact fission-based power source intended for long-duration missions. In the launch corridor, however, this system is not yet contributing to propulsion. Instead, it remains a dormant energy reservoir designed for later activation once the spacecraft is in a stable orbit or in deep space conditions. The distinction between chemical launch energy and nuclear operational energy defines the structure of the entire mission profile. Chemical propulsion provides the initial escape from Earth's gravitational well, while nuclear energy supports sustained operation far from solar intensity. Within the outer atmospheric region, Earth's magnetic field becomes increasingly significant. Charged particles from the ionosphere interact with geomagnetic lines, forming dynamic patterns that extend far into space. These interactions influence space weather, shaping radiation levels that the spacecraft must pass through. Although the nuclear system is shielded, the spacecraft structure itself must account for these energetic particles, ensuring that sensitive electronics remain stable. Shielding materials and layered design help reduce exposure, but the environment itself remains active and variable, driven by solar cycles and geomagnetic fluctuations. The ascent path also passes through regions influenced by residual atmospheric drag, which gradually weakens as altitude increases. The spacecraft's velocity increases under rocket propulsion, and the curvature of Earth becomes more apparent in relation to its trajectory. The surface below transitions from continuous land and ocean patterns to a curved horizon framed by deepening darkness above. This visual transformation corresponds to a physical transition from atmospheric flight to orbital mechanics, where gravitational forces dominate motion in a predictable and continuous curve around the planet. At this stage, the spacecraft is still bound to the immediate influence of Earth. Escape velocity has not yet been achieved and orbital insertion remains ahead. The nuclear system remains in standby condition, monitored through internal diagnostics that ensure stability of temperature, radiation containment, and structural integrity. Engineers design such systems with redundancy, ensuring that no single failure can compromise the containment of nuclear material during launch stress. Vibrational forces, acoustic pressure, and rapid acceleration all act upon the structure as it moves through the last dense layers of atmosphere. The outer environment is also defined by decreasing temperature gradients and increasing exposure to solar radiation. Without the filtering effect of dense air, ultraviolet and higher energy radiation become more prominent. The spacecraft's outer shell reflects and absorbs these energies, maintaining internal stability. The interaction between sunlight and exposed materials produces subtle thermal differences across the vehicle's surface, managed by passive radiators and internal fluid systems that distribute heat evenly. In this region of ascent, time perception remains tied to Earth-based systems. Communication with ground stations continues through relay networks, passing through ionospheric reflections and satellite links. Data flows steadily, including telemetry from structural sensors, propulsion stages, and nuclear system status indicators. Although the nuclear system is not active in propulsion, its monitoring remains essential to ensure safe transition into later mission phases. As the spacecraft moves further into thinner air, the visual presence of Earth's atmosphere becomes faint, blending into the blackness of near space. The boundary is not absolute but gradual, defined by density, energy, and motion, rather than a single physical edge. The spacecraft continues upward, guided by controlled propulsion and precise navigation systems, leaving behind the dense layers where air still behaves as a continuous medium and entering a region where motion is governed primarily by orbital dynamics and gravitational balance. The spacecraft is now situated within controlled engineering environments, where its structural assembly defines the foundation of its mission toward Mars under nuclear-powered design principles. In these facilities, the vehicle is no longer a concept moving through atmosphere, but a tangible system composed of interlocking modules, each built for a specific function. The structure is organized around a central core that houses power distribution, guidance control, and payload integration. Surrounding this core are protective layers designed to manage heat, vibration, and radiation shielding requirements that become essential once nuclear systems are activated in later phases of flight. The assembly process begins with the primary frame, a rigid lattice of lightweight metal alloys selected for their strength-to-weight ratio and stability under extreme temperature variation. These materials are often titanium-based or aluminum-lithium compounds shaped into cylindrical and modular segments that allow for controlled expansion and contraction during launch stresses. Engineers align each segment with precise measurement systems, ensuring that mechanical tolerances remain within extremely narrow margins. Even small deviations could affect vibration harmonics during ascent, so alignment procedures proceed slowly and methodically. Inside this structure, the spacecraft's internal systems are installed in layers. Electrical wiring harnesses form a dense network that connects sensors, processors, and control units. These systems function as the nervous system of the spacecraft, transmitting signals that monitor pressure, temperature, radiation exposure, and structural integrity. The wiring is insulated to prevent electromagnetic interference, especially important in a design that will later operate in proximity to a nuclear power source. Redundant pathways ensure that no single disruption can disable critical communication between subsystems. The nuclear power unit, although not yet active, is integrated within a shielded compartment designed to contain radiation and heat. This compartment is constructed with layered materials that include high-density metals and specialized composites capable of absorbing energetic particles. The containment strategy is based on passive safety principles, meaning that even in the absence of active control, the system remains physically secure. The reactor core, depending on the mission design, may rely on controlled fission reactions that generate heat, later converted into electrical energy through thermoelectric or thermal cycle systems. Thermal management systems are installed alongside the nuclear module. These systems include heat pipes, radiators, and fluid loops that transfer energy away from sensitive components. In space, heat cannot be dissipated through air convection, so radiation becomes the primary mechanism of energy release. Large radiator panels are folded within the spacecraft during launch, and later deployed in space, where they extend outward to release excess thermal energy into the vacuum environment. Their design balances surface area with structural stability, ensuring that they can withstand both launch forces and long-term exposure to space conditions. The spacecraft's propulsion architecture is assembled in parallel with its structural frame. Chemical engines provide initial thrust during launch, while nuclear systems are reserved for sustained deep space operation. This dual architecture reflects the transition between short-duration high-thrust requirements and long-duration efficient propulsion. Fuel tanks are integrated into reinforced sections of the vehicle, containing cryogenic or storable propellants, depending on mission design. These tanks are insulated to reduce thermal loss and equipped with pressure regulation systems that maintain stability during both ground handling and ascent. Navigation and guidance systems are installed within the upper sections of the spacecraft. These include inertial measurement units, star trackers, and computational processors that determine orientation in space. Star trackers function by observing fixed celestial reference points, allowing the spacecraft to orient itself without reliance on Earth-based signals. Inertial systems measure acceleration and rotation, ensuring continuous awareness of motion, even when external references are unavailable. These systems work together to maintain trajectory accuracy during the long journey toward Mars. The integration of the nuclear power system requires strict procedural separation from other assembly stages. Specialized clean zones are established where radiation-sensitive handling protocols are enforced. Technicians operate within controlled environments where temperature, humidity, and particulate levels are carefully regulated. The reactor assembly is transported in shielded containers and installed only after all structural and electronic systems have been verified. This staged approach ensures that the most sensitive components are not exposed to unnecessary mechanical or environmental stress. At the same time, software systems are loaded into the spacecraft's onboard computers. These systems govern everything from propulsion timing to energy distribution and thermal regulation. The software architecture is designed with redundancy and fault tolerance, allowing the spacecraft to continue operating even if individual processors fail. Simulation testing is conducted extensively before integration, replicating conditions of launch vibration, vacuum exposure, and radiation environments expected in deep space. The assembly environment itself is highly controlled. Clean rooms remove dust and microscopic particles that could interfere with mechanical or optical systems. Airflow is regulated to maintain laminar patterns, preventing contamination from settling on sensitive surfaces. Lighting is diffused to reduce thermal gradients across exposed materials. Every stage of construction is documented through sensor logs and visual inspection systems, ensuring traceability of each component from manufacturing to final integration. Structural testing occurs throughout the assembly process. Vibration platforms simulate launch conditions, applying controlled oscillations that replicate the forces of rocket ascent. Acoustic chambers reproduce the intense sound pressure levels experienced during ignition. These tests ensure that the spacecraft can maintain structural integrity when subjected to rapid acceleration and mechanical stress. The nuclear containment system undergoes additional verification, confirming that shielding and isolation remain effective under simulated launch conditions. As the spacecraft nears completion, its external surface becomes fully enclosed, forming a unified aerodynamic shape designed for ascent through the atmosphere. Thermal coatings are applied to protect against heat generated during launch and atmospheric friction. These coatings also contribute to radiation reflection once the spacecraft enters space. The exterior appears smooth and continuous, concealing the complexity of systems beneath its surface layers. Throughout this assembly phase, the nuclear power system remains inactive but continuously monitored. Sensors track temperature stability, structural stress, and containment integrity. Engineers verify that no unintended activation pathways exist and that all safety interlocks function correctly. This careful oversight reflects the importance of controlling energy systems that will eventually support long-duration interplanetary travel. By the end of assembly, the spacecraft represents a complete integration of mechanical, electrical, and nuclear systems. It is no longer a collection of separate components, but a unified structure prepared for transition into launch operations. The balance between chemical propulsion for ascent and nuclear energy for deep space operation defines its architecture. Each subsystem is aligned toward a single purpose: sustained travel beyond Earth toward Mars under controlled and stable energy management principles. The spacecraft now exists within the conceptual and engineered framework of nuclear energy systems that support long-duration space exploration. In this stage of understanding, the focus shifts from physical assembly to the internal processes that allow nuclear power to be transformed into usable energy for spacecraft operation. Nuclear energy in this context originates from the structure of atomic nuclei, where protons and neutrons are bound together by strong nuclear forces. When certain heavy nuclei undergo fission, they split into smaller fragments, releasing energy in the process. This energy emerges primarily as kinetic motion of particles and radiation, which is then converted into heat within a controlled environment. Inside a nuclear reactor designed for space applications, the core contains fuel materials capable of sustaining a controlled chain reaction. These materials are often enriched forms of uranium or other fissile isotopes chosen for their ability to release neutrons when their nuclei split. Each fission event produces additional neutrons, which may then trigger further reactions in a carefully moderated chain. The control of this process is essential, as the rate of reaction determines the stability of energy output. In spacecraft systems, the goal is not explosive release, but steady and predictable energy generation over long periods. The reactor core is surrounded by materials known as moderators and reflectors. Moderators slow down neutrons produced during fission, increasing the likelihood that they will interact with other fissile nuclei rather than escaping the system. Reflectors, on the other hand, redirect escaping neutrons back into the core, improving efficiency. These combined systems ensure that the nuclear reaction remains balanced and self-sustaining, without exceeding safe operational limits. In space applications, this balance is particularly important because external intervention is impossible once the spacecraft is far from Earth. As nuclear reactions occur, energy is released primarily in the form of heat. This heat must be carefully managed and converted into usable power. In spacecraft systems, thermoelectric converters or heat engines transform thermal energy into electrical energy. Thermoelectric systems rely on temperature differences across materials to generate electric current, while heat engines use working fluids that expand and contract through cycles to drive turbines or similar mechanisms. Both approaches are designed for reliability, simplicity, and minimal moving parts, since mechanical failure in space cannot be easily repaired. The nuclear energy system operates within a sealed and heavily shielded environment. Radiation generated by fission, including gamma rays and fast neutrons, is contained using dense shielding materials. These materials absorb or deflect high-energy particles, protecting both onboard electronics and scientific instruments. The shielding also prevents radiation from interfering with navigation systems and communication equipment. The structure of this containment reflects a layered approach where multiple barriers ensure that no single point of failure can expose the spacecraft to uncontrolled radiation levels. Neutron behavior plays a central role in sustaining the reactor process. When a nucleus splits, emitted neutrons travel at high speeds and may either be absorbed by other nuclei or escape the system. Their moderation is critical because slow-moving neutrons are more likely to trigger additional fission events. Materials such as graphite or specialized hydrogen-rich compounds are often used to reduce neutron energy through repeated collisions. This controlled slowing process ensures that the chain reaction remains stable and does not escalate beyond intended limits. The conversion of nuclear energy into electrical power supports all major spacecraft systems. Life support simulations, communication arrays, navigation processors, and thermal regulation units depend on a steady supply of electricity. In a Mars-bound mission, sunlight becomes weaker as distance from the Sun increases, making solar power insufficient for continuous operation. Nuclear energy therefore provides a constant internal source of power that does not depend on external environmental conditions. This independence is one of the key reasons nuclear systems are considered for deep space exploration. Heat generated by the reactor must be continuously transferred away from the core. This is achieved through fluid loops or heat pipes that circulate working substances through the system. As these fluids absorb heat, they carry energy toward radiators located on the spacecraft's exterior. In the vacuum of space, radiators release heat through infrared radiation, allowing energy to dissipate without physical medium. The size and efficiency of these radiators determine how effectively the spacecraft can maintain thermal balance during continuous nuclear operation. The nuclear system is also designed with multiple safety mechanisms. Passive shutdown features ensure that if conditions deviate from expected ranges, the reaction slows or stops automatically without external input. Control rods made of neutron-absorbing materials can be inserted into the reactor core to regulate or halt fission activity. These rods absorb excess neutrons, reducing the probability of further reactions. In spacecraft environments, these safety systems are designed to operate reliably under all conditions, including vibration during launch and microgravity in space. Radiation monitoring systems are embedded throughout the spacecraft. These sensors track neutron flux, gamma radiation levels, and thermal output, providing continuous feedback on reactor performance. Data from these sensors is processed in real time by onboard computers, which adjust control systems to maintain stable operation. This feedback loop is essential for maintaining long-term reliability, especially during extended missions where human intervention is not possible. The nuclear system also influences spacecraft design beyond the reactor itself. Structural components must be arranged to minimize radiation exposure to sensitive instruments. Electronic systems are often placed in shielded compartments or located at a distance from the reactor core. Cable routing and system layout are carefully planned to reduce interference and ensure stable operation of all subsystems. This spatial organization reflects the integration of the nuclear physics principles into engineering design. At this stage of understanding, nuclear energy is not only a power source, but also a system that shapes the entire architecture of the spacecraft. Its presence influences material selection, structural design, thermal management, and mission planning. The controlled release of energy from atomic nuclei becomes the foundation for sustained exploration beyond Earth's immediate environment. Through careful moderation of nuclear reactions and precise conversion of heat into electricity, the spacecraft gains the ability to operate independently across vast distances in space. The spacecraft now exists within a framework where containment and isolation define the boundary between controlled nuclear energy and the surrounding physical environment. At this stage, the focus moves inward from energy generation to the systems that ensure that radioactive materials remain fully separated from crude or electronic components that require absolute stability. Containment layers are not single structures, but multi-tiered barriers, each designed to address different forms of radiation, thermal stress, and mechanical vibration. The architecture reflects a principle of redundancy, where safety does not depend on one system, but on overlapping protections that remain effective under a wide range of conditions. The innermost layer of containment surrounds the reactor core itself. This region is engineered to prevent the release of fissile material even under extreme mechanical stress. The core housing is constructed from dense alloys capable of withstanding both thermal expansion and high-energy particle interaction. Within this housing, fuel elements are arranged in a precise geometry that maintains stable reaction pathways. The arrangement ensures that neutron movement remains predictable, reducing the likelihood of uncontrolled chain reactions. Every surface in this region is designed to endure prolonged exposure to radiation without structural degradation. Surrounding the core housing is a primary radiation shield. This shield is composed of layered materials chosen for their ability to absorb different types of radiation. High-density metals reduce the penetration of gamma rays, while hydrogen-rich compounds slow and capture fast neutrons. These layers are arranged in sequence so that each type of radiation is progressively weakened as it moves outward. The design ensures that by the time radiation reaches outer spacecraft systems, its intensity is reduced to levels that do not interfere with electronics or instrumentation. Beyond the primary shield lies a secondary structural barrier that integrates mechanical protection with additional radiation attenuation. This layer serves as both a physical support structure and a protective buffer. It absorbs vibrations generated during launch and adjusts to thermal expansion differences between internal and external components. The materials used in this region are selected for their ability to maintain integrity under both mechanical stress and prolonged exposure to low-level radiation. This dual function makes the layer essential for long-duration missions where both structural stability and radiation safety must be maintained simultaneously. Thermal insulation is integrated into the containment system as a parallel function. Nuclear reactions generate continuous heat, and without proper management, this energy could accumulate and destabilize internal systems. Insulation layers regulate heat flow, ensuring that thermal energy is directed toward controlled dissipation systems rather than sensitive components. These layers often include reflective surfaces that reduce radiative heat transfer and vacuum-sealed gaps that minimize conduction. The combination of these techniques allows precise control over internal temperature distribution. Control systems are embedded within the containment architecture to actively manage reactor behavior. These systems include sensors that monitor neutron flux temperature gradients and structural stress in real time. Data from these sensors is transmitted to onboard processors that adjust control rods or coolant flow rates as needed. The control rods made from neutron-absorbing materials can be inserted or withdrawn from the reactor core to regulate the intensity of nuclear reactions. Their movement is carefully calibrated to maintain equilibrium between energy production and safety thresholds. Containment integrity is also maintained through passive safety design. This means that even in the absence of active control systems, physical laws ensure that the reactor remains stable. Materials are arranged so that thermal expansion naturally reduces reaction intensity if temperatures rise beyond expected limits. Similarly, gravitational and inertial forces during launch are accounted for in structural design, ensuring that fuel elements remain properly positioned even under extreme acceleration. This passive stability is a critical aspect of nuclear spacecraft safety. The spacecraft's external structure also contributes to containment by providing additional shielding against environmental radiation. In space, cosmic rays and solar particle events can introduce high-energy particles that interact with onboard systems. The outer hull incorporates materials that reduce this exposure, creating a final protective boundary between the nuclear system and the space environment. This hull is not uniform but varies in thickness, depending on proximity to sensitive components. Radiation transport within the containment system follows predictable physical pathways. Neutrons produced in the reactor core undergo repeated collisions with moderator materials, gradually losing energy until they are either absorbed or reach harmless levels. Gamma radiation, being more penetrating, requires dense shielding materials that scatter and absorb photon energy. The layered containment structure ensures that each type of radiation is addressed according to its physical properties, creating a comprehensive protective environment. The integration of nuclear systems within the spacecraft requires careful spatial separation between the reactor and operational modules. Electronics, communication systems, and scientific instruments are positioned at calculated distances to minimize radiation exposure. Cabling and data lines are routed through shielded conduits that prevent electromagnetic interference. This spatial arrangement reflects a balance between compact design and safety isolation, ensuring that all systems can function simultaneously without interference. Containment systems are tested through simulated stress conditions before launch. These simulations include thermal cycling, vibration exposure, and radiation field modeling. Each test verifies that the layered barriers maintain their integrity under combined stress scenarios. Engineers analyze deformation patterns, material fatigue, and shielding performance to confirm that the system behaves as expected. Only after passing these evaluations is the spacecraft cleared for integration with launch systems. Throughout this phase, the nuclear reactor remains in a non-operational or low-power state depending on mission requirements. Activation is carefully controlled and typically delayed until the spacecraft has reached a stable orbital environment. This staged activation ensures that containment systems are not subjected to full operational stress during the most physically demanding phase of ascent. It also allows continuous monitoring of structural integrity before full energy generation begins. The containment architecture therefore represents more than physical shielding. It is an integrated system of materials, geometry, and control logic that ensures nuclear energy remains confined, predictable, and safe under all mission conditions. Every layer contributes to maintaining separation between high-energy nuclear processes and the delicate electronic and structural systems that depend on stable operating conditions. In this way, containment becomes the silent foundation of nuclear-powered space exploration, enabling sustained operation far beyond Earth while preserving internal stability. The spacecraft now exists within the launch phase, where ignition transforms still structures into upward motion, governed by controlled thrust and rapidly changing physical conditions. In this region, the nuclear systems remain inactive or securely isolated, while chemical propulsion provides the primary force required to overcome Earth's gravitational pull. The launch vehicle stands vertically on the surface, integrated with support structures that distribute weight and manage the immense mechanical load imposed by full fuel tanks and multi-stage rocket architecture. Ignition begins in a carefully sequenced process where fuel and oxidizer combine within combustion chambers. This chemical reaction releases energy in the form of high-temperature gases that expand rapidly and are directed through nozzles. The nozzle design converts thermal energy into directed kinetic energy, producing thrust that pushes the spacecraft upward. The initial moments of ignition are defined by increasing pressure vibration and acoustic energy that propagate through both the vehicle structure and surrounding air. As thrust builds, the vehicle transitions from static equilibrium to controlled ascent. The lower atmosphere still contains dense layers of air, so aerodynamic forces are significant. The rocket must push against both gravity and atmospheric drag, requiring maximum thrust during the earliest phase of flight. The structural frame experiences intense vibration as engines reach full power. These vibrations travel through the body of the spacecraft, where damping systems and structural reinforcement reduce the risk of resonance that could damage internal components. During this phase, the nuclear-powered module remains protected within its containment system. It is not involved in propulsion and does not contribute energy to the ascent. Its isolation ensures that all radioactive materials remain stable under high mechanical stress. The separation between chemical propulsion and nuclear systems reflects a fundamental design principle in space engineering, where different energy sources are activated at different mission stages to ensure safety and control. As the rocket rises through the lower atmosphere, air resistance begins to decrease gradually. The vehicle accelerates while maintaining a controlled trajectory guided by onboard navigation systems that adjust engine thrust direction. These adjustments ensure that the ascent path aligns with the intended orbital insertion corridor. Small deviations in angle are corrected in real time using gimbaled engine systems that redirect thrust vectors. The surrounding environment changes rapidly during ascent. Near the surface, air density is high, producing visible exhaust plumes and shock interactions. As altitude increases, the exhaust expands more freely, and the visual appearance of the plume changes from dense and turbulent to more diffuse and elongated. This transformation reflects the decreasing pressure of the surrounding atmosphere. The boundary between aerodynamic flight and near-vacuum conditions becomes increasingly apparent as the vehicle climbs. Thermal loads on the spacecraft vary throughout this phase. The exterior experiences heating caused by air compression and friction, particularly around leading surfaces. Thermal protection systems distribute and dissipate this energy, ensuring that internal structures remain within safe temperature ranges. These systems include layered coatings and insulating materials that slow heat transfer from the outer hull to internal compartments. Meanwhile, internal systems remain thermally regulated through controlled fluid loops and heat exchange units. As the rocket passes through higher atmospheric layers, aerodynamic forces begin to weaken. The vehicle's acceleration becomes more efficient as drag decreases. At this point, the launch system may undergo stage separation, where spent fuel tanks and engines are detached to reduce mass. This process improves efficiency and allows remaining stages to continue accelerating the spacecraft toward orbital velocity. Separation events are carefully timed and executed using explosive bolts or mechanical release systems that ensure clean detachment without destabilizing the trajectory. Throughout ascent guidance systems continuously compute the spacecraft's position, velocity and orientation. Inertial measurement units track acceleration and rotation, while external references assist in maintaining trajectory accuracy. These systems feed data into onboard computers that adjust thrust direction and intensity. The objective is to achieve a precise orbital path that balances gravitational forces with forward velocity, allowing the spacecraft to enter a stable orbit rather than falling back toward Earth. The nuclear system remains in a monitoring state during this entire phase. Sensors track structural stress temperature and radiation containment integrity. Even though it is not active, it is subject to the same mechanical forces as the rest of the spacecraft. Engineers design containment structures to ensure that vibration and acceleration do not compromise internal geometry or shielding alignment. This stability is essential for later activation once the spacecraft is in a controlled space environment. As altitude increases further, the curvature of Earth becomes more pronounced in the background environment. The atmosphere transitions from dense lower layers to thin upper regions, and the sensation of upward motion gradually shifts into orbital mechanics. The rocket's velocity increases to the point where horizontal motion becomes as important as vertical ascent. This balance determines whether the spacecraft will achieve orbit or continue into interplanetary escape trajectory. At the final stage of ascent, the vehicle approaches the boundary where atmospheric influence becomes minimal. Engine thrust continues to guide it into the correct velocity vector for orbital insertion. The surrounding environment is now dominated by near-vacuum conditions, where external air resistance is negligible. The spacecraft is positioned at the threshold between Earth-bound motion and sustained orbital dynamics, preparing for transition into independent spaceflight, where nuclear systems will later support long-duration operation. The spacecraft now transitions into the region where Earth's gravitational dominance begins to loosen in practical terms, even though gravity itself continues to act across vast distances. This phase is defined not by the absence of gravity, but by the increasing role of orbital velocity, where motion around Earth becomes a balance between forward speed and downward pull. The spacecraft, having completed its primary ascent, enters a trajectory designed to reshape vertical climb into sustained orbital motion. The surrounding environment is now near vacuum, with only extremely sparse particles remaining from Earth's upper exosphere. In this outermost atmospheric layer, molecules of hydrogen and helium drift in widely separated paths, no longer behaving as a continuous fluid. Collisions are rare, and motion is dominated by ballistic trajectories influenced by gravity and solar radiation pressure. The spacecraft passes through this environment with minimal aerodynamic resistance, and the physical sensation of air-based motion disappears entirely. What remains is a clean transition into orbital mechanics, where Newtonian motion and gravitational curvature define all movement. The final burn of the launch vehicle plays a critical role in shaping this transition. Engine thrust is adjusted to achieve a precise velocity vector that is nearly horizontal relative to Earth's surface. This orientation is essential because orbital motion depends on lateral speed rather than vertical lift. As thrust continues, the spacecraft gradually tilts its trajectory, converting upward momentum into forward motion. The curvature of Earth beneath becomes more visually and physically significant as the path aligns with orbital parameters. At the moment of engine cut-off, propulsion ceases and the spacecraft is no longer actively pushing against gravity. Instead, it enters a state of free motion, governed entirely by inertia and gravitational attraction. If velocity is sufficient, the spacecraft begins to fall around Earth, rather than directly toward it, creating a stable orbit. This delicate balance defines the boundary between atmospheric flight and sustained orbital presence. Small variations in velocity at this stage determine long-term orbital shape and altitude. The spacecraft's structural systems now experience a different environment. Mechanical stress from acceleration decreases sharply, replaced by micro-vibrations caused by internal systems and thermal adjustments. Temperature differences across surfaces become more pronounced due to alternating exposure to sunlight and shadow. In space, heat transfer occurs only through radiation, so surfaces facing the sun warm gradually, while shaded regions cool. Thermal control systems begin active regulation to maintain internal stability. The nuclear power system remains in a controlled standby or low-output state during early orbit. It is not yet the primary energy source for propulsion, but begins to provide auxiliary power for onboard systems. This transition is gradual, ensuring that all containment and shielding systems are stable in the new environment before full activation. Sensors continue to monitor reactor temperature, structural integrity, and radiation containment, verifying that conditions remain within safe operational limits. Earth's magnetic field becomes increasingly relevant at this altitude. Charged particles trapped within the magnetosphere move along curved field lines, forming radiation belts that extend thousands of kilometers above the planet. The spacecraft passes through regions of varying particle density, where high-energy electrons and protons interact with shielding materials. These interactions are accounted for in design, and sensitive electronics are placed within protected compartments to reduce exposure. Communication systems now rely on direct line-of-sight links with ground stations or relay satellites. Signals travel across vast distances with minimal interference from atmospheric effects. Data transmission includes telemetry from navigation systems, thermal sensors, and nuclear system monitoring units. The spacecraft becomes fully integrated into orbital communication networks, maintaining continuous exchange of information with Earth-based control systems. Navigation in this region relies on precise measurement of velocity and position relative to Earth's center of mass. Small thruster adjustments may be used to correct orbital parameters, ensuring stability and alignment with the intended trajectory toward Mars transfer conditions. These adjustments are subtle but essential, as even minor deviations can accumulate over time and alter interplanetary paths significantly. The spacecraft's orientation is maintained using reaction control systems that expel small amounts of gas to adjust rotation. Without atmospheric resistance, rotational motion persists unless actively corrected. Star trackers provide reference points by observing fixed stellar positions, allowing the spacecraft to determine its orientation with high precision. This system operates independently of Earth, enabling autonomous navigation in deep space conditions. As orbit stabilizes, the spacecraft completes repeated circuits around Earth. Each orbit represents a balance between gravitational pull and forward motion, creating a continuous free-fall state where the spacecraft remains in constant motion without surface contact. The environment outside the spacecraft is silent vacuum punctuated only by radiation and distant light. Earth appears as a curved sphere below, with atmosphere forming a thin, luminous boundary between planet and space. At this stage, the nuclear system becomes increasingly relevant for future mission phases. Although still regulated and partially inactive, it represents the transition from short-term orbital energy dependence to long-term deep space autonomy. The systems that will later support interplanetary travel are now fully present, but remain carefully controlled until the spacecraft exits Earth's immediate gravitational influence. The orbital environment marks the final step before interplanetary departure. The spacecraft is no longer ascending through atmosphere, but instead moving in a stable gravitational path around Earth, preparing for the next phase of trajectory adjustment toward Mars transfer orbit. In this region, motion is governed entirely by orbital mechanics, and all systems are aligned towards sustained stability and readiness for deep space transition. The spacecraft now operates within stable Earth orbit, where motion is governed by continuous freefall, balanced by orbital velocity rather than thrust. In this region, the environment is defined by near-perfect vacuum, with only sparse particles of hydrogen-helium, and trace atmospheric remnants drifting through vast empty space. The spacecraft follows a curved path around Earth, completing repeated cycles that maintain constant altitude and speed unless altered by controlled propulsion adjustments. Gravity remains strong, but its effect is expressed as curvature of motion rather than downward pull. Within this orbital environment, the spacecraft undergoes stabilization procedures that refine its orientation and internal systems after launch stress. Structural vibrations have largely dissipated, leaving only subtle mechanical oscillations caused by internal equipment and thermal cycling. These oscillations are minimal but continuously monitored, as even small shifts in structural alignment can affect long-duration mission accuracy. The spacecraft's frame, having endured launch forces, now operates in a low-stress regime where long-term stability becomes the primary concern. Thermal conditions in orbit are highly dynamic due to alternating exposure to direct sunlight and complete shadow. When the spacecraft faces the Sun, its outer surfaces gradually absorb radiant energy, increasing temperature across exposed panels. When it enters Earth's shadow, heat is lost through infrared radiation into space, causing gradual cooling. This cycle repeats with each orbit, requiring active thermal management systems to maintain internal equilibrium. Heat pipes and radiators distribute energy evenly, preventing localized temperature extremes that could affect sensitive instruments or the nuclear subsystem. The nuclear power system begins a gradual transition toward operational readiness during this orbital phase. Although still carefully controlled, it now contributes auxiliary electrical power to support onboard systems. The reactor remains enclosed within its containment structure, with control mechanisms regulating output levels to ensure stability. Sensors continuously monitor neutron flux thermal gradients and shielding integrity, confirming that all parameters remain within expected operational limits. This cautious activation reflects the necessity of verifying system behavior in a stable orbital environment before full deep space deployment. Radiation conditions in low Earth orbit are complex due to the presence of trapped charged particles within Earth's magnetosphere. The spacecraft passes through regions where high-energy electrons and protons are concentrated in radiation belts. These particles interact with shielding materials, producing secondary radiation that must also be accounted for in system design. The spacecraft's layered protection reduces exposure to sensitive electronics, ensuring that computational systems and communication arrays remain functional despite continuous particle bombardment. Navigation in orbit relies on precise measurement of position and velocity relative to Earth's gravitational field. The spacecraft's onboard computers calculate orbital parameters using data from inertial sensors and external references such as star trackers. These systems allow the spacecraft to maintain accurate orientation without dependence on atmospheric cues. Small adjustments are occasionally made using reaction control thrusters, which emit controlled bursts of gas to modify rotation and maintain directional stability. Communication with Earth remains continuous during orbital operations. Signals are transmitted through ground stations and relay satellites, forming a network that ensures uninterrupted data exchange. Telemetry includes information on system health, orbital parameters, nuclear subsystem status and thermal regulation performance. This constant flow of data allows mission controllers to verify that all systems are functioning as intended before initiating interplanetary transfer procedures. The spacecraft's nuclear system plays an increasingly important role in supporting these communications and onboard computations. As solar energy becomes less reliable due to orbital geometry and potential shadowing events, nuclear-generated power provides a stable and continuous energy source. This independence from solar variability is essential for maintaining consistent system performance, especially during long-duration missions where energy demands remain constant. Orbital mechanics dominate all motion at this stage. The spacecraft's trajectory is a balance between forward velocity and gravitational curvature, creating a continuous path around Earth. Small variations in altitude or velocity can gradually alter orbital shape, so precise control is required to maintain stability. Engineers use predictive models to calculate orbital decay transfer windows and alignment conditions for departure toward Mars. The spacecraft also undergoes system verification processes in orbit. These include diagnostic tests of propulsion, readiness, structural alignment, and nuclear system response under microgravity conditions. Each subsystem is evaluated independently and in coordination with others to ensure full integration. The absence of atmospheric forces allows for highly accurate measurements of system performance, free from the interference of drag or turbulence. As the spacecraft continues its orbital cycles, Earth appears below as a rotating sphere with shifting cloud formations, oceanic patterns, and landmasses passing beneath. The visual perspective reinforces the transition from planetary environment to orbital isolation. The spacecraft no longer interacts with atmospheric systems, but instead exists within a gravitational framework shaped entirely by Earth's mass and motion. The nuclear system remains central to future mission phases, but in orbit it functions primarily as a stabilizing energy source rather than a propulsion mechanism. Its controlled output supports system readiness for the upcoming interplanetary transfer phase. All containment systems remain active, ensuring that radiation remains fully isolated, while operational data confirms steady and predictable behavior. By the end of this orbital stabilization phase, the spacecraft achieves a state of equilibrium in which all systems are synchronized and prepared for departure from Earth orbit. The balance of nuclear power, thermal control, navigation, and structural integrity defines readiness for transition into deep space trajectory toward Mars, where orbital motion around Earth will give way to interplanetary travel governed by solar gravitational dynamics. The spacecraft now enters a phase where sustained operation in deep space begins to define its behavior more than launch dynamics or orbital adjustment. In this environment, Earth is no longer the dominant reference for energy balance or system stability, and the spacecraft relies increasingly on its internal nuclear power source to maintain continuous function. The surrounding space is a near-perfect vacuum with extremely low particle density and minimal thermal conduction, meaning that all energy exchange occurs through radiation and internal transfer systems. At this stage, the nuclear power system becomes a stable and continuous energy generator. The reactor operates under carefully controlled conditions where fission reactions occur at a steady rate, producing heat that is converted into electrical energy. This energy supports all major spacecraft functions, including propulsion system, readiness, navigation, processing, communication, and thermal regulation. Unlike solar power, which varies with distance and orientation, relative to the Sun, nuclear energy provides a constant output independent of external light conditions. The reactor core remains enclosed within its containment structure, where neutron behavior continues to govern the stability of the fission process. Neutrons released during nuclear reactions move through moderator materials that reduce their speed, increasing the probability of further controlled fission events. This moderation process ensures that the energy output remains stable rather than fluctuating unpredictably. The balance between neutron production absorption and leakage determines the overall efficiency of the system. Heat generated in the reactor is transferred through internal fluid loops, designed to move thermal energy away from the core. These fluids circulate through closed pathways, absorbing heat and carrying it toward radiator panels positioned on the spacecraft's exterior. In the vacuum of space, these radiators emit energy as infrared radiation, allowing heat to dissipate without requiring a surrounding medium. The efficiency of this process determines the long-term thermal stability of the spacecraft. The spacecraft's electrical systems now operate primarily on nuclear-derived power. Energy is distributed through regulated networks that supply processors, sensors, communication arrays, and life support simulation systems if applicable. Power conditioning units ensure that voltage and current remain stable, preventing fluctuations that could disrupt sensitive instruments. Redundant circuits provide backup pathways in case of localized failure, maintaining uninterrupted operation across all critical systems. In this deep space environment, thermal conditions are no longer influenced by atmospheric interaction, but by direct solar radiation and internal heat generation. The spacecraft experiences continuous exposure to sunlight on one side and cold darkness on the other. This creates a complex thermal gradient that must be carefully managed. Radiators are oriented and adjusted to maintain balance, ensuring that no region of the spacecraft experiences extreme overheating or excessive cooling. Radiation from cosmic sources becomes a dominant environmental factor. High-energy particles originating from distant astrophysical events permeate interplanetary space. These particles can interact with spacecraft materials, producing secondary radiation and potential electronic interference. Shielding systems within the spacecraft reduce the impact of these particles, while sensitive electronics are placed in protected compartments to minimize disruption. The nuclear system itself is designed to operate safely under this constant radiation background. Navigation systems transition fully to autonomous operation. The spacecraft uses star trackers and inertial measurement units to determine its orientation and velocity in space. Without nearby planetary reference points, the spacecraft relies on fixed stellar positions to maintain directional accuracy. Onboard computers process this data, continuously calculating trajectory adjustments required for the upcoming interplanetary transfer toward Mars. Communication with Earth becomes more dependent on signal timing and distance. As the spacecraft moves farther away, communication delays increase, reflecting the finite speed of light. Data transmission includes system diagnostics, nuclear reactor status, and navigation updates. Despite the increasing distance, the communication link remains stable, supported by deep space tracking networks that monitor the spacecraft's position and trajectory. The spacecraft's structural systems now experience extremely low mechanical stress. Without atmospheric drag or gravitational variation from nearby bodies, the primary forces acting on the structure are thermal expansion and internal system vibration. Materials are selected for long-term stability under these conditions, ensuring that repeated thermal cycling does not degrade structural integrity over time. The nuclear system also begins to play a more direct role in future propulsion planning. While not yet used for thrust generation, its energy output supports systems that prepare for potential nuclear thermal or nuclear electric propulsion modes. These advanced propulsion concepts rely on converting reactor heat or electrical output into directed thrust, enabling more efficient travel across interplanetary distances than traditional chemical propulsion. At this stage, the spacecraft exists in a stable deep space operational state, where all systems are synchronized under continuous nuclear energy supply. The balance between power generation, thermal control, radiation shielding, and autonomous navigation defines its ability to function far from Earth. The environment around it is vast, quiet, and largely empty, with only faint traces of solar particles and distant radiation fields crossing its path. The transition from Earth-centered orbit to deep space cruise is now fully established. The spacecraft no longer depends on planetary systems for energy or guidance in any immediate sense. Instead, it operates as an independent structure, moving through interplanetary space sustained by controlled nuclear reactions and guided by precise computational navigation systems that prepare it for the long trajectory toward Mars. The spacecraft now moves through an environment defined primarily by radiation, rather than matter, where empty space is filled with invisible energetic particles originating from the Sun and distant cosmic sources. In this interplanetary region, solar radiation extends outward as a continuous stream of charged particles known as the solar wind. These particles include protons and electrons that travel through space at high speeds, shaped by the Sun's magnetic field. Although sparse compared to atmospheric density near Earth, their constant presence creates a dynamic, energetic environment that influences spacecraft systems over long durations. Beyond solar particles, the spacecraft is exposed to galactic cosmic radiation. These particles originate from distant astrophysical events such as supernovae and energetic galactic processes. They carry extremely high energy and can penetrate spacecraft materials more deeply than lower energy solar particles. When these particles interact with shielding structures, they may produce secondary particle cascades including neutrons and gamma radiation. The spacecraft's design accounts for these interactions through layered shielding and strategic placement of sensitive components. The nuclear-powered system operates continuously within this radiation environment, requiring careful separation between external radiation sources and internal nuclear reactions. The reactor core produces its own controlled radiation in the form of neutrons and gamma emissions, but this is fully contained within shielding systems. External radiation adds an additional layer of complexity, as it introduces unpredictable energetic interactions that must be managed without interfering with internal nuclear stability. The distinction between internal and external radiation environments becomes essential for long-term operational safety. Shielding materials within the spacecraft are designed to address multiple types of radiation simultaneously. Dense metals reduce penetration of high-energy photons, while hydrogen-rich materials slow fast neutrons through repeated collisions. This layered approach ensures that both internally generated and externally arriving radiation are progressively attenuated before reaching sensitive electronics. The effectiveness of this shielding depends on thickness composition and geometric arrangement around critical systems. As the spacecraft moves farther from Earth, it exits the protection of the planet's magnetosphere. This transition removes a significant natural barrier that previously deflected many charged particles. Without this shielding, the spacecraft experiences the full intensity of interplanetary radiation. This increase is gradual but continuous, requiring adaptive monitoring systems that track radiation levels in real time. Sensors distributed across the spacecraft measure particle flux, energy distribution, and cumulative exposure over time. The nuclear system remains stable within this environment, but it must account for radiation-induced effects on surrounding materials. High-energy particles can gradually alter the properties of structural components, a process known as radiation damage. Over time, this can affect material strength, electrical conductivity, and thermal behavior. Engineers mitigate these effects by selecting radiation-resistant materials and designing redundancy into structural and electronic systems. Energy produced by the nuclear reactor continues to support all spacecraft operations. This energy is converted into electricity and distributed across multiple subsystems, including navigation, communication, and thermal control. The stability of nuclear power becomes increasingly important as solar energy diminishes with distance from the Sun. At this stage of interplanetary travel, sunlight is weaker and less reliable as a primary energy source, reinforcing the importance of internal nuclear generation. Thermal conditions in this region are governed almost entirely by radiation exchange. The spacecraft absorbs solar energy on surfaces facing the Sun, while simultaneously losing heat through infrared emission into space. This creates a continuous thermal balance that must be actively managed. Radiator systems adjust orientation to optimize heat rejection, ensuring that internal systems remain within operational temperature ranges despite external fluctuations. Cosmic radiation interactions can produce secondary particles that contribute to the spacecraft's internal radiation environment. When high-energy particles strike shielding materials, they may generate neutrons that travel short distances before being absorbed. These secondary effects are carefully modeled and monitored as they can influence both nuclear system measurements and electronic performance. The interplay between primary and secondary radiation becomes a key factor in long-term mission stability. Navigation systems continue to operate autonomously, relying on star tracking and inertial measurement. In deep space, the absence of nearby planetary landmarks makes stellar references essential for maintaining orientation. The spacecraft continuously compares observed star positions with internal maps to determine its orientation in three-dimensional space. This system remains highly stable despite the radiation environment, as optical sensors are shielded and calibrated to resist particle interference. Communication with Earth is now subject to significant signal delay due to increasing distance. Data transmission requires precise timing and high-gain antennas to maintain signal integrity across millions of kilometers. Despite these challenges, telemetry continues to flow steadily, providing information on reactor status, system health, and trajectory updates. This communication link remains essential for long-term mission monitoring, even as the spacecraft becomes increasingly autonomous. The radiation environment also influences long-term material behavior within the spacecraft. Over extended periods, exposure to high-energy particles can gradually alter molecular structures in polymers and other materials. This process occurs slowly but is continuously accounted for in mission design. Materials are selected for durability under prolonged radiation exposure, ensuring that structural integrity is maintained throughout the journey to Mars. At this stage, the spacecraft exists in a balanced state between internal energy generation and external radiation exposure. The nuclear system provides a stable and controlled energy source, while shielding systems mitigate the effects of cosmic and solar radiation. Navigation, communication, and thermal control systems all operate within this energetic environment, maintaining stability as the spacecraft continues its interplanetary trajectory. The transition through radiation-dominated space defines this phase of the mission. There is no atmospheric influence, no aerodynamic force, and no gravitational perturbation beyond the broad pull of the Sun and planets. Instead, the spacecraft exists within a field of energy interactions where particles, radiation, and nuclear processes define its operational reality. This environment remains stable but continuously active, shaping the long journey toward Mars. The spacecraft now operates in a region of interplanetary space where navigation is defined entirely by gravitational fields and calculated motion rather than immediate physical guidance. The Sun becomes the dominant gravitational reference point, shaping trajectories across vast distances. In this environment, the spacecraft follows a carefully computed path that balances solar gravity with its initial velocity, creating a stable interplanetary transfer route toward Mars. There is no atmospheric resistance, no external mechanical interference, only continuous motion through a vacuum shaped by celestial mechanics. Navigation in this phase relies on precise mathematical modeling of orbital dynamics. The spacecraft's onboard systems calculate its position relative to both Earth and the Sun using continuous streams of sensor data. Inertial measurement units track acceleration and rotation, while star trackers provide fixed celestial references. These two systems work together to maintain a stable internal coordinate framework that allows the spacecraft to determine its exact orientation in space at any given moment. The trajectory toward Mars is not a straight line but a curved path shaped by orbital mechanics. The spacecraft follows a transfer orbit that intersects the orbital path of Mars at a carefully predicted future point. This requires precise timing as both Earth and Mars are moving continuously around the Sun at different speeds and distances. The spacecraft must arrive at the correct location in space at the correct time to enter Martian gravitational influence successfully. Small trajectory correction maneuvers are performed during this phase using onboard thrusters. These adjustments are extremely subtle compared to launch propulsion, involving minor changes in velocity that accumulate over long periods. Each correction is calculated based on updated positional data and predictive modeling. The absence of atmospheric forces allows these adjustments to remain highly accurate, as there is no external drag to distort motion once applied. The nuclear power system plays a central role in sustaining these navigation processes. Continuous electrical energy generated by the reactor supports onboard computing systems that process trajectory calculations. Without nuclear power, long-duration interplanetary navigation would be limited by energy availability, especially as solar intensity decreases with distance from the Sun. The reactor provides a stable and independent energy source that ensures uninterrupted computational capacity. Thermal conditions in this region of space remain governed by radiative exchange. The spacecraft absorbs sunlight on surfaces facing the Sun while simultaneously emitting heat into deep space. This creates a persistent thermal gradient that shifts slowly as orientation changes. Thermal control systems adjust radiator positioning to maintain equilibrium, ensuring that internal components remain within stable operating ranges. Without atmospheric buffering, even small imbalances in heat distribution must be actively corrected. Radiation from the Sun continues to influence spacecraft conditions, although its intensity decreases with distance. The solar wind remains present as a flow of charged particles, but its density diminishes as it expands outward. The spacecraft still encounters these particles, though less frequently than in regions closer to Earth. Galactic cosmic radiation remains constant, providing a steady background of high-energy particles that interact with shielding materials over time. Communication with Earth becomes increasingly delayed as distance grows. Signals transmitted between the spacecraft and ground stations take longer to travel, reflecting the finite speed of light. Despite this delay, communication remains continuous and structured. Telemetry includes updates on nuclear reactor performance, navigation status, and system health. Ground-based controllers monitor this data, while the spacecraft continues to operate autonomously between communication intervals. The spacecraft's orientation system remains essential for maintaining directional accuracy. Without atmospheric cues or nearby physical references, orientation is determined entirely through star tracking and inertial measurement. The spacecraft continuously observes fixed stellar positions and compares them to onboard reference maps. This allows it to maintain stable orientation even during minor rotational disturbances caused by internal system movements or external particle impacts. The nuclear system continues steady operation, providing energy for all onboard systems. Its output remains regulated to match demand, ensuring that no excess heat or electrical fluctuation occurs. Sensors monitor reactor stability, confirming that neutron activity remains within controlled limits. This stable energy production is essential for sustaining long-duration navigation communication and thermal regulation far from any external energy source. Trajectory corrections continue at planned intervals, ensuring that the spacecraft remains aligned with its intended Mars transfer path. These corrections account for gravitational influences from other planetary bodies, solar radiation pressure, and minor variations in the initial launch conditions. Even small deviations, if left uncorrected, could result in significant positional errors over interplanetary distances. The spacecraft now exists in a state of sustained interplanetary cruise. It is no longer influenced by Earth's immediate gravitational environment, yet it remains within the broader gravitational field of the Sun. Its motion is steady, predictable, and governed by well-understood physical laws. Nuclear energy supports continuous system operation, enabling autonomy and stability across the vast distances between planets. In this phase, the spacecraft represents a balance between energy, motion, and precision. Nuclear power sustains internal systems, while gravitational mechanics define external motion. Navigation systems maintain direction through continuous calculation, and thermal systems regulate environmental exposure. All components function together in a synchronized structure designed for long-duration travel through space toward Mars. The spacecraft now operates in an environment where thermal balance becomes one of the most persistent and subtle challenges of interplanetary travel. In deep space, heat does not move through air or fluid, but only through radiation. Every surface that faces the Sun receives a steady stream of electromagnetic energy, while every shaded surface simultaneously releases heat into the cold vacuum of space. This creates a continuous and uneven exchange of energy that must be carefully managed to prevent both overheating and excessive cooling within the spacecraft. The thermal control system is built around the principle of controlled redistribution rather than simple insulation. Heat generated by onboard electronics propulsion, readiness systems, and the nuclear power unit is captured by internal loops filled with thermally conductive fluids. These fluids circulate through the spacecraft, absorbing energy from warmer regions and transporting it toward radiator structures located on the exterior. The movement is slow and continuous, designed to maintain stability rather than rapid adjustment. Radiators function as the primary interface between internal energy and deep space. Their surfaces are engineered to maximize emission of infrared radiation while minimizing absorption of incoming sunlight. In the vacuum environment, heat leaves the spacecraft in the form of electromagnetic waves that travel outward indefinitely. The efficiency of this process depends on surface area orientation and material properties. Radiator panels are often extended into large, thin structures to increase their ability to release heat without adding excessive structural mass. As the spacecraft travels farther from Earth, solar intensity gradually decreases, but it does not disappear. Sunlight still provides a significant source of external heating, especially on surfaces directly exposed to the Sun. The spacecraft slowly rotates or adjusts orientation to distribute this energy evenly across its structure. Without atmospheric moderation, even small imbalances in exposure can lead to significant temperature differences over time. The nuclear power system introduces a steady internal heat source that must be continuously regulated. Unlike solar heating, which varies with orientation and distance, nuclear-generated heat is constant, and originates from within the reactor core. This heat is transferred through controlled systems that ensure it does not accumulate in sensitive areas. The balance between nuclear heat production and radiator heat loss defines the spacecraft's internal thermal equilibrium. Within the reactor system, thermal energy is a byproduct of controlled fission reactions. The energy released during these reactions is absorbed by surrounding materials and converted into usable heat flow. This heat is then directed into power conversion units that generate electricity for spacecraft operations. However, not all thermal energy is converted. Excess heat must still be removed to maintain safe operating conditions. This makes thermal management an inseparable part of nuclear power operation in space. The absence of an atmosphere means that conduction and convection are effectively non-existent outside the spacecraft. Heat cannot dissipate into surrounding gas, nor can it be carried away by fluid motion. This makes radiation the only viable mechanism for thermal loss. As a result, even small increases in internal energy must eventually be balanced by increased radiative emission. This constraint shapes every aspect of spacecraft thermal design. Temperature differences across the spacecraft surface are managed through careful structural layout. Components that generate heat, such as processors and power converters, are positioned near thermal pathways that lead to radiators. Sensitive instruments are isolated within insulated compartments that maintain stable conditions regardless of external fluctuations. This separation ensures that critical systems remain unaffected by localized thermal variations. As the spacecraft continues its journey toward Mars, it experiences gradual shifts in thermal environment due to changing distance from the Sun. Although the decrease in solar intensity is slow, it is continuous. This requires the thermal control system to adapt dynamically over time, adjusting radiator orientation and internal fluid flow rates to maintain equilibrium. These adjustments occur without interruption to other spacecraft operations. Radiation from the Sun continues to play a role in thermal dynamics. Even in deep space, solar photons carry enough energy to influence surface temperatures. The spacecraft's orientation relative to the Sun determines how much energy is absorbed at any given time. Surfaces facing away from the Sun radiate heat into the cold background of space, which is effectively near absolute thermal emptiness. This contrast creates a persistent gradient that the spacecraft must continuously manage. The nuclear system remains a stable contributor to both power and thermal output. Its operation is carefully balanced so that energy production does not exceed the capacity of the thermal rejection system. Sensors continuously monitor temperature at multiple points within the reactor and surrounding structures. If any region begins to exceed safe thresholds, adjustments are made to redistribute heat or modify reactor output levels. Thermal control also interacts with radiation shielding systems. Some shielding materials absorb both radiation and heat, creating localized thermal loads that must be accounted for in overall system design. These materials are integrated into the spacecraft structure in a way that allows heat to flow toward radiators without compromising radiation protection. This dual function reflects the complexity of managing multiple environmental factors simultaneously. Over time, the spacecraft reaches a stable thermal rhythm. Internal systems generate predictable heat loads. Radiators maintain consistent emission rates, and external solar input follows a gradual decline pattern. This equilibrium allows the spacecraft to maintain long-duration stability without major thermal fluctuations. Even small variations are absorbed through continuous adjustment rather than abrupt correction. In this phase of interplanetary travel, thermal control becomes a silent but constant background process that supports every other system. Navigation, communication, and nuclear energy generation all depend on maintaining stable temperature conditions. Without this balance, electronic systems could drift out of calibration. Structural materials could expand or contract unpredictably, and reactor performance could become unstable. The spacecraft continues forward through deep space, maintaining a delicate balance between internal heat generation and external radiative loss. The thermal system does not dominate motion or navigation, but it ensures that all other systems remain within functional limits. In this way, thermal control becomes an invisible framework supporting the continuity of long-duration nuclear-powered space travel toward Mars. The spacecraft now enters the long cruise phase between Earth and Mars, where motion becomes steady, quiet, and largely unchanged over extended periods of time. In this region of interplanetary space, there are no atmospheric forces, no structural vibrations from launch, and no rapid shifts in gravitational influence. The spacecraft follows a predetermined transfer orbit around the Sun, shaped by the initial departure conditions from Earth and refined through earlier trajectory corrections. Its path is stable, governed by predictable celestial mechanics that unfold over months of continuous travel. The Sun remains the central gravitational anchor of this journey. The spacecraft moves along a curved trajectory that gradually shifts outward from Earth's orbital path toward the orbital path of Mars. This transfer orbit is not a straight line but an elongated arc, carefully aligned so that both the spacecraft and Mars will occupy the same region of space at the same time in the future. The precision of this alignment depends on small but critical adjustments made earlier in the mission, ensuring that long-term orbital mechanics guide both bodies toward convergence. During this cruise phase, the spacecraft operates almost entirely under autonomous control. The distance from Earth is now large enough that communication delays become significant, and real-time intervention is no longer practical. Onboard systems take full responsibility for navigation, thermal regulation, power management, and scientific instrumentation. The nuclear power system provides a constant and reliable energy source that enables this autonomy, maintaining continuous operation without dependence on solar intensity or external input. The reactor continues to produce steady thermal energy through controlled fission processes. This energy is converted into electrical power that sustains all onboard systems. The consistency of nuclear output allows the spacecraft to maintain stable performance across the entire cruise phase. Unlike solar arrays, which would diminish in effectiveness with increasing distance from the Sun, the nuclear system remains unaffected by position within the solar system. This independence becomes essential for long-duration missions extending beyond Earth orbit. Thermal conditions during cruise remain defined by radiative exchange with the environment. The spacecraft absorbs sunlight on its forward-facing surfaces while simultaneously emitting heat into deep space through radiators. The balance between absorbed and emitted energy shifts slowly as the spacecraft moves farther from the Sun. This gradual change requires continuous adjustment of thermal control systems to maintain stable internal conditions. The process is gradual but constant, forming a background rhythm of energy regulation. The surrounding environment is largely empty, yet not entirely devoid of influence. Solar wind continues to flow outward from the Sun, carrying charged particles that move through space at high speeds. The density of this particle flow decreases with distance, but its presence remains detectable by onboard sensors. Galactic cosmic radiation continues to permeate the environment, introducing high-energy particles that occasionally interact with spacecraft shielding. These interactions are infrequent but persistent, forming a continuous low-level energetic background. Inside the spacecraft, systems operate in a stable configuration. Electrical networks distribute nuclear-generated power to navigation computers, communication arrays, thermal systems, and scientific instruments. Redundant circuits ensure that no single failure can disrupt critical functions. Computational systems run continuous calculations to refine trajectory predictions and monitor system health. These calculations account for gravitational influences from the Sun and occasional perturbations from other planetary bodies. Navigation during cruise relies on a combination of inertial measurement and stellar observation. Star trackers observe fixed points of light in the sky and compare them to internal reference maps. This allows the spacecraft to determine its orientation with high precision. Inertial systems track acceleration and rotation, ensuring continuity between observational updates. Together, these systems maintain a stable navigational framework that does not depend on Earth-based guidance. The spacecraft's structural condition remains stable under extremely low mechanical stress. Without atmospheric drag or significant gravitational variation, the primary forces acting on the structure are thermal expansion and internal system vibration. These forces are minimal and predictable, allowing materials to maintain long-term integrity. The absence of external mechanical stress contributes to the overall stability of the spacecraft during the extended cruise period. Communication with Earth continues, but at increasing intervals due to signal travel time. Data transmitted from the spacecraft include system diagnostics, nuclear reactor status, thermal balance information, and navigation updates. Ground systems receive this information and store it for analysis, while response commands are prepared for future transmission windows. This asynchronous communication structure becomes a defining feature of deep space operations. The nuclear system remains central to sustaining all spacecraft activity. Its stable energy output ensures that no interruptions occur in critical systems, even during extended periods of communication delay or solar variability. The reactor operates within tightly controlled parameters, maintaining equilibrium between energy production, heat generation, and radiation containment. Continuous monitoring ensures that all values remain within expected operational limits. As the spacecraft progresses along its transfer orbit, its position relative to both Earth and Mars changes slowly but continuously. Earth gradually recedes into the background of space, while Mars becomes more prominent as a destination point ahead along the orbital path. This gradual shift is not visible as rapid motion, but as a slow change in relative positioning over time governed entirely by orbital mechanics. The cruise phase represents a period of sustained stability in which all systems function in coordinated balance. Nuclear energy provides uninterrupted power, thermal systems maintain equilibrium, navigation systems preserve trajectory, accuracy, and communication systems sustain contact with Earth across vast distances. The spacecraft continues its journey through interplanetary space, moving steadily along a path defined by gravitational forces and long-term orbital alignment toward Mars. The spacecraft now approaches the region of interplanetary space where Mars's gravitational influence begins to gradually shape its trajectory in subtle but increasingly important ways. Although still primarily governed by the Sun's gravity, the spacecraft's motion begins to reflect the presence of a second planetary system ahead. Mars appears not as a stationary target but as a moving gravitational body following its own orbit around the Sun. The spacecraft and Mars are both in continuous motion, and their eventual alignment depends on carefully maintained orbital timing established long before this phase of travel. As distance from Earth increases further, the spacecraft exists in a quieter region of space where solar radiation is weaker and particle density is extremely low. The environment is still not empty, but the influences are sparse and widely distributed. Solar wind continues as a thin stream of charged particles, while galactic radiation persists as a constant background presence. These factors no longer dominate spacecraft behavior, but remain important considerations for long-term system stability and material resilience. Navigation systems continue to refine the spacecraft's trajectory with increasing precision. The approach toward Mars requires careful alignment with the planet's orbital path and timing window for gravitational capture. Small corrections are performed using onboard thrusters, each adjustment calculated based on updated positional data and predictive models. These corrections are extremely subtle, often involving minute changes in velocity that accumulate over long periods to produce significant directional refinement. The nuclear power system remains the central energy source supporting all onboard operations. Its steady output allows continuous computation communication and thermal regulation without dependence on external energy sources. The reactor operates within a stable regime where fission reactions produce controlled heat, converted into electricity through internal energy conversion systems. This consistent energy supply is essential during the approach phase, where navigation accuracy and system reliability must be maintained without interruption. Thermal conditions continue to evolve gradually as the spacecraft moves farther from the Sun. Although solar heating decreases the spacecraft, still experiences uneven thermal exposure depending on orientation. Surfaces facing the Sun absorb energy, while shaded regions radiate heat into deep space. Radiators adjust orientation to maintain thermal balance, ensuring that internal systems remain within operational temperature ranges. The nuclear system adds a steady internal heat contribution that must also be continuously managed through the same thermal pathways. As Mars becomes more prominent in the spacecraft's forward trajectory, gravitational modeling becomes increasingly refined. The spacecraft is now within a region where Mars's gravity begins to slightly influence its path, even though it remains outside the planet's immediate sphere of strong gravitational dominance. This transitional region requires precise calculations to ensure that the spacecraft will enter the correct approach corridor for orbital insertion or potential landing sequences in later mission phases. Communication with Earth continued to function, but signal delays are now significantly longer due to increased distance. Data transmissions include navigation updates, reactor status reports, and system health diagnostics. Ground control receives this information asynchronously, meaning that all interactions occur with a delay that reflects the finite speed of light. Despite this delay, communication remains stable and continuous, supporting long-term mission oversight. Inside the spacecraft, systems operate in a highly coordinated and autonomous configuration. Navigation, thermal control, communication, and power systems function as an integrated network managed by onboard computational units. These systems rely on predictive algorithms that anticipate future conditions based on current trajectory and environmental data. This predictive capability becomes increasingly important as real-time intervention from Earth becomes less practical. The spacecraft's structural integrity remains stable under long-duration exposure to deep space conditions. Without atmospheric pressure or mechanical turbulence, structural stress is minimal. The primary influences on the spacecraft structure are slow thermal cycling and minor adjustments caused by internal system operation. Materials are selected for long-term durability under radiation exposure and repeated temperature variation, ensuring that no gradual degradation compromises mission safety. Radiation exposure remains a constant background condition. Solar particles are less intense at this distance, but galactic cosmic radiation continues to permeate the environment. These high-energy particles interact occasionally with spacecraft shielding, producing secondary particles that are absorbed or deflected by internal protective layers. Over time, cumulative exposure is monitored to to ensure that electronic systems remain within safe operational limits. The nuclear system continues to operate in a stable and controlled state, providing all necessary energy for spacecraft function. Its output supports navigation calculations, communication systems, thermal regulation, and onboard diagnostics. Continuous monitoring ensures that reactor behavior remains predictable and that containment systems maintain full integrity. The system is now fully integrated into the spacecraft's long-duration operational framework, functioning as its primary energy foundation. As Mars draws closer in orbital alignment, the spacecraft enters a phase of increasingly precise trajectory matching. The objective is no longer simple forward motion through interplanetary space, but controlled synchronization with the planet's gravitational field. This requires careful timing so that when the spacecraft reaches the correct spatial region, Mars will be positioned to capture it within its gravitational influence. The spacecraft now moves through a narrowing corridor of space where both solar and Martian gravitational forces must be considered simultaneously. This region marks the transition from general interplanetary cruise to targeted planetary approach. All onboard systems are now focused on maintaining trajectory accuracy and preparing for the next phase of orbital insertion or descent planning, depending on mission design. In this stage of the journey, the spacecraft remains stable, autonomous, and fully powered by nuclear energy, continuing its silent and controlled movement through deep space toward Mars, guided by precise calculations and the steady influence of celestial mechanics. The spacecraft now enters the approach corridor where Mars' gravitational influence becomes the dominant factor, shaping the final phase of interplanetary travel. In this region of space, motion is no longer defined primarily by a simple heliocentric path, but by a combined interaction between the Sun's gravity and the increasing pull of Mars. The spacecraft's trajectory gradually bends toward the planet, forming a carefully calculated arc that must align with Mars's position at a precise moment in time. This alignment is the result of long-range planning that accounts for both orbital mechanics and small variations accumulated during the cruise phase. Mars appears gradually larger in the forward field of motion, not as a static object, but as a moving body embedded in its own orbital path around the Sun. The spacecraft must match not only position, but also relative velocity to enter a stable capture condition. This requires continuous refinement of trajectory data, using onboard systems that integrate real-time sensor readings with predictive orbital models. Even minor deviations at this stage can significantly alter the outcome of orbital insertion, making precision essential. The nuclear power system continues to provide stable and uninterrupted energy for all spacecraft operations. Its output supports continuous computation, communication, and thermal regulation as the spacecraft enters this more dynamic gravitational environment. The reactor remains fully contained, operating within a controlled regime where fission reactions generate consistent heat that is converted into electrical power. This energy stability allows navigation and propulsion systems to respond quickly to updated trajectory calculations without delay. Thermal conditions begin to shift more noticeably as the spacecraft approaches Mars. Solar radiation is weaker than near Earth, but still sufficient to create directional heating on exposed surfaces. At the same time, internal heat generated by the nuclear system remains constant. This combination creates a complex thermal environment where both external and internal sources must be balanced continuously. Radiators adjust their orientation in response to changing conditions, releasing heat into space to maintain internal stability. Radiation from the Sun continues to decrease in intensity with distance, but it remains a relevant factor in spacecraft design. Solar particles are less dense here, yet still capable of interacting with spacecraft materials. galactic cosmic radiation remains steady, forming a persistent energetic background that passes through interplanetary space without significant attenuation. Shielding systems continue to protect sensitive electronics from cumulative exposure, ensuring that long-term operation remains unaffected. Navigation systems now operate with increased sensitivity, as small positional errors can have large consequences during planetary approach. Star trackers continue to provide fixed reference points, while inertial measurement units track subtle changes in velocity and orientation. These systems work together to maintain precise alignment with the planned Mars intercept trajectory. Onboard computers continuously update calculations to account for gravitational influences from both Mars and the Sun. Communication with Earth remains functional but increasingly delayed. Signals now require longer travel times, and the spacecraft operates with a higher degree of autonomy. Ground control receives updated telemetry that includes reactor performance data, trajectory status, and system diagnostics. Due to the time delay, all critical decisions must be executed on board, based on pre-programmed instructions and adaptive algorithms, rather than immediate external input. As the spacecraft moves deeper into Mars' gravitational sphere of influence, orbital dynamics become more complex. The spacecraft is no longer simply following a solar orbit, but transitioning into a trajectory shaped significantly by the planet ahead. This phase requires careful control of velocity to ensure that the spacecraft is captured into a stable orbit, rather than passing too close or missing the target entirely. The nuclear system remains central to maintaining this precision. Its continuous energy output ensures that all computational and control systems remain active without interruption. Thruster adjustments, when required, are executed using stored propellant and guided by nuclear-powered control systems. These adjustments are extremely small but critically important, fine-tuning the spacecraft's path to ensure correct alignment with Mars's gravitational field. Thermal management continues to operate in a balanced state with radiators and internal circulation systems maintaining equilibrium between heat generation and heat loss. As the spacecraft nears Mars, subtle changes in solar intensity and reflected planetary radiation begin to influence thermal distribution. These effects are minor but continuously monitored to ensure system stability. The visual presence of Mars becomes increasingly prominent. Its surface features atmospheric layers, and overall planetary structure become more distinct as distance decreases. The spacecraft approaches not as a direct descent vehicle, but as an object entering a complex gravitational system where timing and velocity determine the nature of capture. The interaction between spacecraft motion and planetary gravity defines the final approach corridor. At this stage, all spacecraft systems operate in a tightly coordinated configuration. Navigation, propulsion, readiness, thermal regulation, communication, and nuclear energy production function as a unified system preparing for orbital insertion. Each subsystem contributes to maintaining stability during the most sensitive phase of interplanetary travel. The spacecraft now exists at the threshold between interplanetary cruise and planetary capture. Mars's gravitational field is no longer a distant influence, but an active shaping force on its trajectory. The balance of motion, energy, and control is maintained with increasing precision as the spacecraft prepares for the final transition into Mars orbit, where interplanetary travel will give way to planetary system integration. The spacecraft now enters the final transition phase where Mars' gravitational field becomes the dominant influence on its motion, reshaping its trajectory from interplanetary travel into planetary capture. In this region, the balance between forward velocity and gravitational pull becomes increasingly delicate. The spacecraft is no longer moving through a simple solar transfer path, but through a complex gravitational interaction zone, where Mars, the Sun, and residual interplanetary forces all contribute to its final approach behavior. The timing of arrival is critical as Mars continues its own orbital motion, requiring precise synchronization between spacecraft position and planetary location. As the spacecraft draws closer, Mars's gravitational influence steadily increases, bending the trajectory into a controlled arc. This is not a sudden change, but a gradual reshaping of motion over time. The spacecraft must reduce its relative velocity at the correct moment to allow Mars's gravity to capture it into orbit. This process depends on both pre-calculated trajectory design and real-time adjustments made by onboard systems. Even small variations in speed or angle can determine whether the spacecraft enters stable orbit, performs a flyby, or misses the capture window entirely. The nuclear power system continues to operate as the primary energy source throughout this critical phase. Its steady output ensures that all onboard systems remain fully functional without interruption. Navigation computers, propulsion control systems, thermal regulation networks, and communication arrays all depend on this continuous energy supply. The reactor remains fully contained within its shielding structure, operating under stable conditions, where fission reactions generate controlled heat that is converted into electrical energy. This stability is essential during a phase where precision and timing are most critical. Thermal conditions near Mars become slightly more complex due to the combination of reduced solar intensity and increasing influence from reflected planetary radiation. Mars emits and reflects energy from its surface and thin atmosphere, creating subtle variations in the thermal environment around the spacecraft. Although these effects are relatively small compared to solar input, they are continuously measured and integrated into thermal control models. Radiator systems adjust their orientation to maintain equilibrium between internal heat generation and external energy exchange. Radiation conditions remain dominated by galactic cosmic rays and residual solar particles. The spacecraft now operates beyond the protective influence of Earth's magnetosphere and experiences a stable but persistent background of high-energy particles. These particles pass through space continuously, occasionally interacting with shielding materials and producing secondary radiation effects. The spacecraft's layered protection systems ensure that these interactions do not disrupt electronic systems or nuclear reactor stability. Navigation becomes increasingly sensitive as the spacecraft enters Mars' capture zone. The spacecraft's onboard systems continuously refine its trajectory using updated measurements of position, velocity, and gravitational influence. Star trackers provide fixed spatial references while inertial systems monitor motion changes with high precision. Together, these systems allow the spacecraft to maintain accurate alignment with the planned orbital insertion path. Computational models predict how Mars's gravity will alter the spacecraft's motion over time, guiding necessary adjustments. Communication with Earth is now significantly delayed due to distance, but still continuous. Signals carry information about system status, nuclear reactor performance, trajectory updates, and thermal conditions. Ground control receives this data as part of a long-term monitoring process, rather than immediate operational control. The spacecraft operates with full autonomy, executing pre-programmed sequences and adaptive responses based on onboard sensor data. As Mars's gravitational pull strengthens, the spacecraft's velocity relative to the planet begins to decrease naturally as it is drawn into a curved capture trajectory. This deceleration is not caused by atmospheric drag but by gravitational interaction alone. The spacecraft's path bends inward, transitioning from a solar orbit into a Mars-centered trajectory. This moment marks the shift from interplanetary travel to planetary orbital insertion. The nuclear system remains stable throughout this transition, continuing to supply uninterrupted energy for all critical functions. Its role becomes especially important as the spacecraft prepares for potential orbital maneuvering or descent-related operations. Thruster systems guided by nuclear-powered control units make final adjustments to ensure correct orbital parameters. These adjustments are minimal, but essential, fine-tuning the spacecraft's velocity and angle of approach. Thermal and structural systems remain stable under these conditions. Without atmospheric interference, the spacecraft experiences no aerodynamic stress, only gradual changes in thermal exposure and gravitational influence. Materials respond predictably, maintaining structural integrity as the spacecraft transitions into Mars' gravitational domain. Internal systems remain synchronized, ensuring that all subsystems operate in coordinated balance. Mars now fills a larger portion of the spacecraft's forward view, its surface features becoming more distinct as distance decreases. The planet is no longer a distant target, but an active gravitational environment into which the spacecraft is being drawn. The final adjustments in trajectory determine whether the spacecraft will enter a stable orbit, prepare for surface operations, or continue into an alternative orbital path depending on mission design. At this concluding stage, the spacecraft exists in a fully autonomous nuclear-powered state of operation within Mars' gravitational influence. All systems, navigation, thermal control, communication, and energy production function in synchronized stability. The interplanetary journey from Earth is complete in trajectory terms, and the spacecraft now transitions into Mars orbital integration, marking the end of its long passage through deep space and the beginning of sustained planetary presence.